Welcome to the NMR course. Please note that on RE Connected there are workbooks and solutions, and at the end of every lecture I would like you to visit that workbook and to engage with the problems that are in them. So by the end of this lecture you need to be able to deal with question 1 in the workbook, and there are 5 problems to solve in question 1. Now, when we speak of NMR, or nuclear magnetic resonance, it's interesting to compare it to other techniques. We're going to look at a little bit of Mass Spec in this course towards the end of the course, but mainly NMR. And they are really powerful techniques. So yes, IR is a powerful technique. It gives functional groups, but NMR gives more and provides the structure of a molecule that's available to you. So it provides a map of a carbon-hydrogen framework. Mass spectrometry gives something different. It gives molecular weight and fragmentations, but hopefully by the end of this course you'll be fully aware of the power of both of these techniques. Now, the central equation for NMR is the Larmor Equation. And nuclear magnetic resonance is all about the nucleus of atoms. So if you take some atoms together with their nuclei, which it's not possible to do otherwise, if you place them in a magnetic field, some nuclei will absorb electromagnetic radiation in the radio frequency range. Some will, some won't. But if they do, then the Larmor frequency is given by the gyromagnetic ratio that's specific to the nucleus times the magnetic field all over 2 pi. And you can look in tables for gyromagnetic ratio for several nuclei. So for example, for the nucleus of a hydrogen atom, which is simply a proton, remember hydrogen atoms only got a proton as its nucleus, so a proton has a gyromagnetic ratio of 26.75 times 10 to the 7 radians per second per Tesla. Remember, don't forget that it is quite a large number. That 10 to the 7 is often omitted in tables, as placed at the head of tables, so don't forget to use it. But if you wanted to calculate the frequency at which a hydrogen nucleus resonates in a magnetic field, you need to look up the gyromagnetic ratio. You need to know the field strength of the magnet you're placing that hydrogen atom into, and you divide by 2 pi to get the Larmor frequency. Okay. Just please note that sometimes this gyromagnetic ratio is sometimes called the magnetic gyric ratio. Those are the same things. Okay. Right. Now, just I would like you to be aware of what electromagnetic radiation is being absorbed. And if here's our spectrum, our electromagnetic spectrum, and we've got visible light in the middle, and we've got gamma rays on the right and radio waves on the left, I want you to note that NMR, the type of electromagnetic radiation that's absorbed, that frequency, that Larmor frequency, is in this region over here. It's in the the region of radio waves, and this is the lowest energy part of the spectrum. So what I'm trying to say here is that NMR is a very insensitive technique, and there are always strategies to try and improve NMR. The electronics gets more modern and more sensitive by the year, but also one way we can try and improve this low energy is to use stronger magnets, because if I go back to the Larmor equation, if you use a stronger magnet, you use a higher field strength magnet, the frequency is going to be higher. You'll be in a slightly higher energy, but still in the radio waves region of electromagnetic spectrum. Just to give you some historical context, that old NMR instruments used a permanent magnet, and we used to have an instrument that looked like this with a permanent magnet in, and of course that's what we need because we need a magnetic field to place the nuclei in, and then they will absorb radiation. But the way they works slightly different to the way modern NMR spectrometers work. So how these would work is that a frequency close to the Larmor frequency would be generated. And so at a high frequency, notice the spectrum is back to front now. High is on the left and low is on the right. Let's start at a high frequency. As you change the frequency, you see if you're not at the exact Larmor frequency, you see nothing happen. So even when you're close to absorption, you see there's no absorption in the spectrum, but the moment you hit the correct frequency, you'll see the absorption, and then when your frequency becomes too low, there's still no absorption, and by the time you reach the end, you have your NMR spectrum. So this is the old way that NMR spectra used to be run. Things change. We still get the same spectra with modern instruments, but spectra are acquired in a slightly different manner. Spectra are still always plotted with high frequency on the left, low frequency on the right. It's convention, but things are done slightly differently. So I've put a snail here just to illustrate. It's quite a slow process. You scan, and the slower you scan, the more precise you can sometimes get your spectra. Now, of course, now we don't have permanent magnets as a block of ferrite anymore. What we do is we have superconducting magnets, and we've got 3 of them in our department. And what happens is there's a great big, inside the magnet, here's a cutaway of what a magnet container looks like. There's a great big coil of wire that can have many tens of kilometers of wire wound and wound around. And what that wire does is that it's a superconducting wire, and it carries a current. And if a current flows in that wire, it will generate a magnetic field. Now, we choose superconductors because there's no resistance to current. So if you start the current flowing in that superconductor, it won't stop. But of course, the superconductor used is niobium-3 tin, and of course it only is a superconductor at liquid helium temperatures. So of course, this long, big coil of superconductor is placed in a tank of liquid helium that maintains a low temperature so that the current will continue to flow in that coil and generate a magnetic field. Now, helium is very expensive, so there are vacuum regions to try and protect the helium from radiation, from thermal conducting heat into it. And of course there are tanks on the outside filled with liquid nitrogen, and that liquid nitrogen protects the liquid helium from boil off. And so you have these 2 containers with liquid nitrogen and liquid helium, and the liquid helium helps the superconductor to properly superconduct. This means that you can build up very high magnetic fields. The current here can be hundreds of amps, and so your field can be very strong. So the modern way is not to use a block of ferrite permanent magnets for your NMR, but to use these powerful superconducting magnets. Okay. Right, in the department we've got 3 magnets at different field strengths. We've got a 7 Tesla magnet, a 9.4 Tesla magnet, and a 14 Tesla magnet. Now, for the hydrogen nucleus, which I said was a proton, we can use the Larmor equation. We've got everything we need. We've got the magnetic gyric ratio, which we can place in here. We've got the magnetic field. We can use this equation 3 times to calculate the Larmor frequency at 3 times, and we know what 2 pi is. We can work that. So you can try this as an exercise. You can try and calculate the Larmor frequency for all 3 different B0 magnet strengths. And your answers should be 300 megahertz, 400 megahertz, and 600 megahertz. Now, it's interesting that when it comes to NMR instruments, we don't normally describe magnets by their field strength in Tesla. we normally describe them by their proton Larmor frequency. And so sometimes we'll refer to these three magnets as the 300 megahertz instrument, the 400 megahertz instrument, and the 600 megahertz instrument. What that means is that they have the correct field strength to make a proton resonate at those particular frequencies. Of course, if you've got carbon-13 and you place it in any of those instruments, carbon-13 is not going to resonate at those frequencies. Carbon-13 will resonate at something at very different frequencies to that. Okay. Right. So how modern NMR works is that you provide a huge pulse of energy, and that pulse of energy is absorbed by all nuclei. So if you, it's a very short pulse for about 10 microseconds at a very high power level, and you pulse it for that short amount, all nuclei will receive energy. So this is how modern NMR works, is that you pulse, very, very sharp pulse, and all nuclei receive energy. And then you turn off all signals to the sample, and you listen, and then coming back from the sample after pulsing it, you'll get your signal coming back. And your signal will look something like this, which is a free inductive decay. You see it's strong and it decays with time. And that's the NMR signal that you will get from your sample. Of course, this looks nothing like an NMR spectrum that we had from the continuous wave. We can't see the absorption at the Larmor frequency, and in fact even seeing the Larmor frequency is going to be a problem. So there's a technique that's done. If we do this pulse and detect, there's a technique that is used, and the technique that is used is the Fourier Transform. I can see in this signal coming from the NMR that there is what appears to be a pure frequency. You can see the wavelength is constant all the way through. It's just decaying with time, so I see it's got quite a high frequency too. A Fourier Transform will pick that out and say, and tell you exactly what frequency that is. So the axis here is on time axis, and your axis here is a frequency axis, and you see on the left is high frequency, and so we've definitely got a high frequency in this signal. You could get a signal like this, for example. You can see that the wavelength is long and the frequency is low, and so when you perform a Fourier Transform on this signal, you'll get a single line corresponding to low frequency, and so a Fourier Transform transforms your signal into an NMR spectrum and shows whether you've got a high frequency or a low frequency. Of course, you might have a mixture of frequencies, and if you've got a mixture of frequencies, you can see the overarching low frequency coming through, and the very fine high frequency that's overlaid with it. The Fourier Transform will pick that up, and you will see two signals corresponding to a high on the left and a low on the right. Running NMR like this is fantastic because you can acquire many of these and add them together, and your signals add and your noise cancels out, so you increase your signal to noise ratio when you run NMR like this. Okay, so just quick summary of where we are at. So please, there's a Larmor equation. Please, we need to check where we are. There are two ways to absorb magnetic resonance. You can use continuous wave, which is one frequency at a time. Pulsed NMR excites all frequencies, and of course if you do that, if you use pulsed NMR, you get an FID, and you will have to Fourier transform it to produce the spectrum. Right, so please, what you need to do at the end of this lecture is you need to go to the workbook and you need to answer the question 1, and you can check your answer at the back. The solution manual is in the back. Check that you get the correct Larmor frequencies or the correct magnetic direct ratios where you have to calculate those.